All right, so now that we've made all the code changes to get BERT running with DeepSpeed and gone all over all of that, let's now actually run it. So let's see, so in terms of our outline, we've covered these top 3 pieces now. And now we're just going to go over kind of some performance impact of different features with DeepSpeed and use this BERT model that we just went over to actually run this. So specifically, first we want to talk about single GPU performance, a few different features that DeepSpeed has, and we'll show kind of the impact of those. And then we'll move on to multi-GPU, multi-node kind of situation and kind of show the impact of different interconnect speeds and all that stuff. So first here, we're on our worker node. So let's go into our DeepSpeed examples, and then inside there we have our Bing BERT example. So let's see. So the first thing we want to look at is our DeepSpeed config. And let's run this with FP32, so this is full precision, so we're going to turn off this feature that runs in FP16. We are going to, I know, I guess from prior experience with this, but sometimes it's a little trial and error, so you need to figure out what your sort of best micro batch size is per GPU. So in this case, we're going to run with 1 GPU, and we're going to run with a micro batch size of 32. And that means with 1 GPU, that would be a total batch size, train batch size of 32 as well. Okay, and we have this handy run script created just for kind of this tutorial today, but this will run DeepSpeed. We're going to include just 1 worker node and then 1 GPU on that worker node. And we're going to execute this DeepSpeed train script, which is what we just went over. We have this this BERT large lamb JSON, which I'll bring that back up just as a refresher as well. But the key kind of piece here is the DS config here is turning on and off all these features. So this is what we just looked at. That's we're going to use like full precision training, batch size of 32, all that stuff. So when we run this, it's going to just run on a single GPU with this config. And let's turn off our transformer kernels. So we'll just be running this with basic PyTorch kernels here. And let's see, this looks good. And let me bring this up. So this is the, whoops. This is the sort of BERT config pointing to kind of our training data and learning rate schedule stuff for sequence 128 training at least. Validation data and everything. Cool, so let's go ahead and run this. So again, this is just running on 1 machine. If we scroll up, we can see right here at the top that the world size is 1. We've loaded some training data here, this path, number of samples, how long it took. Kind of gives us a summary of what our DeepSpeed JSON config looks like. So you can kind of see that for your logging purposes later, and also all sorts of other different parameters, what they're set to. And this should start. What we can do too is go to this other node, go to worker 1, see what's going on. Cool, so we see that 1 GPU is being used on a memory. Go, looks like we started. And in this case, what we see after about 50 steps, this is pretty slow, so this is full precision. This is running at about 43-ish samples per second. Let's let it hit 100 steps and then we'll kind of close this out. But we can use this as kind of a baseline for what we see so far. So let's make a note of this. So this is FP32, 1 GPU, batch size 32 gets us about 43 samples per second. Make this a little bigger for the video. Cool, so we can keep track of this. Okay, let's close this out. The one thing I like to do just to be on the safe side is run this parallel SSH script and just kill all Python processes to kind of make sure that everything's essentially been closed down. And then we can check the running processes as well. Looks like we're good. Okay, so next thing we want to do is let's turn on FP16. So that's simply just change this one line in our JSON config now. And from prior experience, I also know that we can, in this case, we can bump up our batch size. So this means that our input batch size and our model weights and everything are changing from full precision to half precision. So we can actually fit more now in memory. So this, along with a few other things, actually gives us a nice speed improvement. But let's check that out. So everything else can be the same. Let's just run this here. Right, some logging, somewhat verbose. So we see FP16 enabled is true here, so that's great. Doing this data loading just like we did before. Now we're just about to start training. Cool, wow, okay, great. So now we're if we recall previously what we were at is, so this is one GPU, batch size of 64, now yields us about 179 samples a second. And if we look at NVIDIA SMI again, yeah, we see we might have a little bit more room to increase the batch size a little bit if we wanted to kind of push the boundaries here, but it's pretty high, right? All right, so now let's do one more thing. So this has been running 150 steps. So we can see that it's running reasonably fast. We're getting sort of printouts more often of the throughput and such. So let's kill this. Make sure everything's killed, looks good. We can even verify, sometimes nice, just to make sure that everything's kind of been cleaned up okay. There's nothing allocated on our GPUs, that's great. So now let's go ahead and turn on our DeepSpeed transformer kernels. So in this case, we're turning on this flag to replace our BERT layers with DeepSpeed's version of the transformer kernel. And we're also going to use this stochastic mode, gives us a slight speed improvement as well. But I urge you to check out, so we have these, as a reminder here, we have these 2 pages on our DeepSpeed website that kind of go into a big deep dive, and also Tanji previously talked about this, I believe, in this workshop or this tutorial as well. So some of the features of this. But cool, so all we need to do, at least for this code, is just to add these 2 flags. Everything else essentially stays the same. Now let's run this. So while we wait, let's update our log. So this is FP16 plus kernels, 1 GPU, same batch size. What are we going to get? Cool. Looks good. Let's let it do one more. One thing I want to note here as well is the performance that we see on this machine. This is essentially a DGX1 box. If we compare that to our numbers here that we did for this sort of ultra-fast BERT end-to-end run, they're a little bit different. And the reason for that, and I verified this several times, the reason for this is the machines that we're using here are actually DGX2 boxes. So DGX2s have a handful of different kind of improvements over DGX1s, but in general, we see about a 5-ish% boost in throughput per GPU, or for a single GPU, comparing a DGX1 versus a DGX2. But cool, so yeah, we're about 215. So let's kill this and this. So that's pretty great in terms of single GPU. Now, one other thing is, if you notice here, so let's do this other feature, which is wall clock breakdown. So what wall clock breakdown is going to do is it's going to give us a breakdown of time for each of the components of training. So this is going to give us information on forward pass, backward pass, and optimizer step, and also our gradient reduction step if we're training across multiple GPUs. So let's redo this same run. Let's make sure everything's good. Okay. Do the same run, but now just turning on this wall clock breakdown. Excellent. Let me just kill this so we. Okay. So let me scroll up. There's a lot here, but let's just take one sample here of this. So this is showing in milliseconds, forward time, backward time, and our step time. So what we see is every step, or every training step, is doing some optimizer update. So that means that our DS config here is showing a micro batch size of 64, and then every 64 samples we do an optimizer step. So what we could do is, to improve some of this performance, is turn on gradient accumulation steps, and let's do this to 10, let's say. So now I've put an underscore here just to turn off this. Essentially, I just comment this out. So now our effective batch size for this one GPU training is going to be 640, so 64 times 10. So what this will do is it'll essentially, we can kind of amortize the optimizer time over multiple steps. What we'll show in a little bit is this also helps us in our gradient, reducing our gradient reduction time. So on like low bandwidth clusters and stuff as well. But let's try this again now with gradient accumulation set. So now this is FP16 plus kernels plus, and then one GPU, batch size 64, but our gradient accumulation steps are 10. Now, oh, we left wall clock breakdown on. Okay, so it's going a little bit fast through there, but let's find a samples per second. This is kind of hard to see. Let's just turn this on. Sorry about that. Back off. Okay, let's rerun this. What we're expecting here is that just this samples per second is going to boost up a little bit since we're not taking a hit on the optimizer time every training step. The trade-off is that now we're increasing the total batch size a bit, which might have some convergence issues, or yeah. So cool. Right off the bat, we're 236. So that increases our performance slightly, which is nice. Excellent. Okay, so now let me close this. And let's move on to multi-node, multi-GPU. So we have this other worker over here just sitting idle, right? And 7 other GPUs on this box. So let's see what happens as we increase that. So let's bring up our dsconfig again. And we can then, let's turn this off. And so what we actually want to train with in the batch size that we used for the speed run is 64K. So what that means is 65,536. So now each of our 16 GPUs will be running, but microbatch size is 64, and then for a total batch size with gradient accumulation of 64K. What's nice is DeepSpeed will actually calculate the appropriate number of gradient accumulation steps needed to satisfy these 2 constraints. So you don't have to worry about that. And let's see. So now, if we go back to our DS run, one important change here is now we want to run on the entire job, which remember is everything in our job host file. So here, so worker 0, worker 1, both 8, and we will run this with our transformer kernels. It's good. This will also be with some gradient accumulation steps, which is nice. And let's give this a try. So if we see here, world size, saying 16. Oops, I think there was an issue here. Fun part about a live recording here. Okay. So the issue is on our other node. You notice we do not have the same JSON. So this is kind of the issue with the fact that this doesn't have a shared file system. So we have to make sure when we make changes on this node, we propagate those files to the other node as well, either through a shared file system or just SCP them over. So let's go ahead and do that. Specifically, the only thing we've changed here is the dsconfig JSON. So let's do that to worker 0. And the path is here. And we can verify that's over there. Looks good. Now, let's try again. Cool. Lots of logs printing out here. Okay, we're loading our training data set. And notice also we have worker 1 here, worker 0, so we're getting all the logs from all 16 ranks here. And let's go ahead. It looks like we've started to train. So let's look at NVIDIA SMI on this other node. Excellent. So we have a little bit of headroom just like before, but looking good. All the GPUs seem to be working away there. Excellent. So now we're seeing about 3,700 samples per second. Let's go here. So what do we see now per GPU is, so this update our notes here, we have, this is 16 GPUs, batch size, microbatch size 64. And what we see with that is about, let's say 3680 samples per second, which translates to 230 per GPU, which is pretty good. It's popping back up here about 37, but yeah, so what's nice here is we're seeing pretty great scalability, I guess, in terms of as we scale from 1 GPU to 16 GPUs. Then InfiniBand's helping us here, NVLink between GPUs on the single blocks is helping us. Lots of good stuff here. So let me cancel this. I want to show you one more thing relating to this model. And I have another job set of nodes allocated. So this is on a completely different cluster. And what's going on here, I have the same code, but this is a kind of slower cluster. So look, it's a different SKU or instance type on Azure, where we have 4 Tesla V100 cards, but only with 16 gigabytes of memory per card. And we have 4 GPUs per node. So in this case, if we look at our job host file, we have 4 worker nodes, each with 4 GPUs. So still have 16 GPUs in total, but we are kind of spreading that across multiple nodes. The other thing is, if we look at IBstat, there's no InfiniBand. We also can look at, I have an iPerf session server running on one of the other nodes. So this is going to do just a basic TCP test to transfer some data between worker 0 and worker 1. So we can kind of get a basic idea of the throughput available, at least via TCP. It's pretty low. So it's, in this case, it's, if we're being generous, maybe 4 gigabits per second, right? But let's see what we can do here. So I'm going to, so we have a different JSON file here. But first, let's try, so in this case, since we only have 16 gigs of memory, we're going to run with a batch size, micro batch size of 32, so that we can actually fit this. And then let's first try gradient accumulation steps of 1. So in this case, our train batch size will actually be calculated as follows. So we're going to, will be 32 times 1 in this case, times 16. So our total train batch size that DeepSpeed will calculate for this and use is 512. This is commented out, so we're not actually using this yet. We're still using LAM optimizer. We're using FP16. We're still going to use our kernels, everything like that. So we'll show this is the run script, kind of looks similar to the other one on the other cluster. We're going to use our transformer kernel, stochastic mode. Yeah, essentially all the same, but just this different cluster with different interconnects and smaller GPU memory. So let's just make sure there's nothing else running. Looks good. Let's launch the training and see what happens. Scroll up, missed it. Just gonna show you the world size, but didn't pop up. Let's see, I think I can get it from up here though. So this, so world size here is 16, micro batch 32, train batch size here calculated is at 512. Let's go to the bottom. So I started this with this wall clock breakdown, which is actually great. Open this up a little bit more. So this isn't showing our samples per second yet, but what we see, if we look kind of closely at our all reduced time, so this is backward all reduced microstep. So what this is showing is in milliseconds. So we're taking almost 3 seconds, 3 full seconds to just do the gradient reduction. So if you recall, what's happening is each rank was going to compute its own backward pass of the samples that it's seen. It'll generate its gradients, and then it will all reduce those gradients across all ranks. So there's a communication kind of synchronization point, and then proceed to the next step. Here we go, samples per second, 167. So let's see. So this is 16 GPUs, V100, 16 gig, slow interconnects. So 16 GPUs, batch size 32, gradient accumulation steps 1 gets us about 167 samples a second. This was 16 GPUs too, so like, right, so like this is gonna be 167 divided by 16, like 10 samples per second per GPU, right? This is pretty bad. Okay, so now if we close out of this, if we can get away with running a larger effective batch size, total effective batch size, which we can, this should save us a lot, right? So if let's comment out gradient accumulation steps. We're going to do our train batch size per GPU is 32. Total train batch size this. Just let's show you here 1 second. So if we do some quick math, that's total train batch size divided by micro batch size 32 divided by 16 GPUs. So now 128. So what this means is we're going to do, each GPU is going to do 128 forward and backward passes by itself without coordinating between any other GPUs. And then after it's done 128 of them, it'll do the gradient reduction, which will sort of be that synchronization point, which takes 3 seconds, right? Which 3 seconds is an eternity, right? Like in these sorts of things. So let's see what happens. This should be good. Let's verify. So, yep, that looks good. Now let's make sure that's all good. We can even do this across the whole cluster or the job. If we don't see any other processes running, that's great. And let's just load our launch script. So remember this, we're not passing any include or exclude. So this means that we're gonna run over all 16 GPUs. And let's check it out. So now this is same setup, but 128 gradient accumulation steps. And what's that going to give us? So what we'll see, oh, it's going kind of fast. That's good, but it's a little hard to read. So let me kill this. Okay, if we scroll up and see what happened, 3,500 samples per second. What is that? That's pretty wild. Let's rerun that really quick. But I want you to be able to see what's happening. So let me turn off wall clock breakdown. Make sure everything's killed. Okay. I think that's at 3,500, right? That's pretty big difference. But let's double check. So we're in the model initialization. Yeah, look at that. That's great. We could almost fully train this thing now, right? Okay, so 35, 30 samples per second. What's the per GPU? 220. Excellent. That was in the realm of what we were seeing on the per GPU on the 32. That's great. Okay, so it looks like we've dropped a little bit. Ah, yes, okay, so this is an important point. So remember, our gradient accumulation steps are 128. So that means right around 120, 130, there's a drop, right? Because we just spent 3 seconds to do that all reduced, right? So if this samples per second that DeepSpeed outputs here is averaged over time. So if we let this run for a while, we'll kind of converge on the true average, right? But let's, even if we go with the low end, so this is like the 2947. Let's be conservative here. 47. What is that? 2947 divided by 16, 184. Still excellent. And what is that? 184 divided by 10? Easy math, I guess, but 18x improvement by just increasing our gradient accumulation steps. Not bad. Cool. All right. So I think that's about it for the BERT related stuff that we wanted to go over today. So yeah, we'll take a pause for now, and I'll come back with a few other things relating to Megatron and Zero.